Earth's magnetic field, also known as the geomagnetic field, is the magnetic field that extends from the Earth's interior to where it meets the solar wind, a stream of charged particles emanating from the Sun. Its magnitude at the Earth's surface ranges from 25 to 65 microtesla. Roughly speaking, it is the field of a magnetic dipole currently tilted at an angle of about 10 degrees with respect to Earth's rotational axis, as if there were a bar magnet placed at that angle at the center of the Earth. Unlike a bar magnet, however, Earth's magnetic field changes over time because it is generated by a geodynamo. The north and south magnetic poles wander widely, but sufficiently slowly for ordinary compasses to remain useful for navigation. However, at irregular intervals averaging several 100,000 years, the Earth's field reverses and the north and south magnetic poles relatively abruptly switch places. These reversals of the geomagnetic poles leave a record in rocks that are of value to paleomagnetists in calculating geomagnetic fields in the past. Such information in turn is helpful in studying the motions of continents and ocean floors in the process of plate tectonics. The magnetosphere is the region above the ionosphere and extends several tens of thousands of kilometers into space, protecting the Earth from the charged particles of the solar wind and cosmic rays that would otherwise strip away the upper atmosphere, including the ozone layer that protects the Earth from harmful ultraviolet radiation. Importance: Earth's magnetic field serves to deflect most of the solar wind, whose charged particles would otherwise strip away the ozone layer that protects the Earth from harmful ultraviolet radiation. One stripping mechanism is for gas to be caught in bubbles of magnetic field, which are ripped off by solar winds. Calculations of the loss of carbon dioxide from the atmosphere of Mars, resulting from scavenging of ions by the solar wind, indicate that the dissipation of the magnetic field of Mars caused a near-total loss of its atmosphere. The study of past magnetic field of the Earth is known as paleomagnetism. The polarity of the Earth's magnetic field is recorded in igneous rocks, and reversals of the field are thus detectable as stripes centered on mid-ocean ridges where the seafloor is spreading, while the stability of the geomagnetic poles between reversals has allowed paleomagnetists to track the past motion of continents. Reversals also provide the basis for magnetostratigraphy, a way of dating rocks and sediments. The field also magnetizes the crust, and magnetic anomalies can be used to search for deposits of metal ores. Humans have used compasses for direction finding since the 11th century AD and for navigation since the 12th century. Although the north magnetic pole does shift with time, this wandering is slow enough that a simple compass remains useful for navigation. Variations in the magnetic field strength have been correlated to rainfall variation within the tropics. Main characteristics, description. At any location, the Earth's magnetic field can be represented by a three-dimensional vector. A typical procedure for measuring its direction is to use a compass to determine the direction of magnetic north. Its angle relative to true north is the declination or variation. Facing magnetic north, the angle the field makes with the horizontal is the inclination or dip. The intensity of the field is proportional to the force it exerts on a magnet. Another common representation is in x, y and z coordinates. Intensity. The intensity of the field is often measured in gauss, but is generally reported in nanotesla, with 1 G equals 100,000 ENT. A nanotesla is also referred to as a gamma. The tesla is the SI unit of the magnetic field, B. The field ranges between approximately 25,000 and 65,000 ENT. By comparison, a strong refrigerator magnet has a field of about 100 gauss. A map of intensity contours is called an isodynamic chart. As the 2010 World Magnetic Model shows, the intensity tends to decrease from the poles to the equator. A minimum intensity occurs over South America while there are maxima over northern Canada, Siberia, and the coast of Antarctica south of Australia. Inclination. The inclination is given by an angle that can assume values between -90° to 90°. In the northern hemisphere, the field points downwards. It is straight down at the north magnetic pole and rotates upwards as the latitude decreases until it is horizontal at the magnetic equator. it continues to rotate upwards until it is straight up at the south magnetic pole. Inclination can be measured with a dip circle. An isoclinic chart for the Earth's magnetic field is shown below. Declination. Declination is positive for an eastward deviation of the field relative to true north. It can be estimated by comparing the magnetic north-south heading on a compass with the direction of a celestial pole. Maps typically include information on the declination as an angle or a small diagram showing the relationship between magnetic north and true north. Information on declination for a region can be represented by a chart with igonic lines. Geographical variation. Components of the Earth's magnetic field at the surface from the World Magnetic Model for 2010. Dipolar approximation. Near the surface of the Earth, its magnetic field can be closely approximated by the field of a magnetic dipole positioned at the center of the Earth and tilted at an angle of about 10 degrees with respect to the rotational axis of the Earth. The dipole is roughly equivalent to a powerful bar magnet, with its south pole pointing towards the geomagnetic north pole. This may seem surprising, but the north pole of a magnet is so defined because, if allowed to rotate freely, it points roughly northward. Since the north pole of a magnet attracts the south poles of other magnets and repels the north poles, it must be attracted to the south pole of Earth's magnet. The dipolar field accounts for 80–90% of the field in most locations. Magnetic poles. The positions of the magnetic poles can be defined in at least two ways, locally or globally. One way to define a pole is as a point where the magnetic field is vertical. This can be determined by measuring the inclination, as described above. The inclination of the Earth's field is 90 degrees at the north magnetic pole and -90 degrees, downwards, at the south magnetic pole. The two poles wander independently of each other and are not directly opposite each other on the globe. They can migrate rapidly. Movements of up to 40 km per year have been observed for the North Magnetic Pole. Over the last 180 years, the North Magnetic Pole has been migrating northwestward, from Cape Adelaide in the Buovia Peninsula in 1831 to 600 km from Resolute Bay in 2001. The magnetic equator is the line where the inclination is zero. The global definition of the Earth's field is based on a mathematical model. If a line is drawn through the center of the Earth, parallel to the moment of the best-fitting magnetic dipole, the two positions where it intersects the Earth's surface are called the north and south geomagnetic poles. If the Earth's magnetic field were perfectly dipolar, the geomagnetic poles and magnetic dipoles would coincide and compasses would point towards them. However, the Earth's field has a significant non-dipolar contribution, so the poles do not coincide and compasses do not generally point at either. Magnetosphere. Earth's magnetic field, predominantly dipolar at its surface, is distorted further out by the solar wind. This is a stream of charged particles leaving the Sun's corona and accelerating to a speed of 200 to 1,000 km per second. They carry with them a magnetic field, the interplanetary magnetic field. The solar wind exerts a pressure, and if it could reach Earth's atmosphere it would erode it. However, it is kept away by the pressure of the Earth's magnetic field. The magnetopause, the area where the pressures balance, is the boundary of the magnetosphere. Despite its name, the magnetosphere is asymmetric, with the sunward side being about 10 Earth radii out but the other side stretching out in a magnetosphere that extends beyond 200 Earth radii. Sunward of the magnetopause is the bow shock, the area where the solar wind slows abruptly. Inside the magnetosphere is the plasmasphere, a donut-shaped region containing low-energy charged particles, or plasma. This region begins at a height of 60 km, extends up to 3 or 4 Earth radii, and includes the ionosphere. This region rotates with the Earth. There are also two concentric tire-shaped regions, called the Van Allen radiation belts, with high-energy ions. The inner belt is 1–2 Earth radii out while the outer belt is at 4–7 Earth radii. The plasmasphere and Van Allen belts have partial overlap, with the extent of overlap varying greatly with solar activity. As well as deflecting the solar wind, the Earth's magnetic field deflects cosmic rays, high-energy charged particles that are mostly from outside the solar system. By contrast, astronauts on the Moon risk exposure to radiation. Anyone who had been on the Moon's surface during a particularly violent solar eruption in 2005 would have received a lethal dose. Some of the charged particles do get into the magnetosphere. These spiral around field lines, bouncing back and forth between the poles several times per second. In addition, positive ions slowly drift westward and negative ions drift eastward, giving rise to a ring current. This current reduces the magnetic field at the Earth's surface. Particles that penetrate the ionosphere and collide with the atoms there give rise to the lights of the aurora and also emit X-rays. The varying conditions in the magnetosphere, known as space weather, are largely driven by solar activity. If the solar wind is weak, the magnetosphere expands. While if it is strong, it compresses the magnetosphere and more of it gets in. Periods of particularly intense activity, called geomagnetic storms, can occur when a coronal mass ejection erupts above the Sun and sends a shock wave through the solar system. Such a wave can take just 2 days to reach the Earth. Geomagnetic storms can cause a lot of disruption. The Halloween storm of 2003 damaged more than a third of NASA's satellites. The largest documented storm occurred in 1859. It induced currents strong enough to short out telegraph lines, and aurorae were reported as far south as Hawaii. Time dependence, short-term variations. The geomagnetic field changes on timescales from milliseconds to millions of years. Shorter timescales mostly arise from currents in the ionosphere and magnetosphere, and some changes can be traced to geomagnetic storms or daily variations in currents. Changes over timescales of a year or more mostly reflect changes in the Earth's interior, particularly the iron-rich core. Frequently, the Earth's magnetosphere is hit by solar flares causing geomagnetic storms, provoking displays of aurorae. The short-term instability of the magnetic field is measured with the K-index. Data from Themis show that the magnetic field, which interacts with the solar wind, is reduced when the magnetic orientation is aligned between Sun and Earth, opposite to the previous hypothesis. During forthcoming solar storms, this could result in blackouts and disruptions in artificial satellites. Secular variation. Changes in Earth's magnetic field on a timescale of a year or more are referred to as secular variation. Over hundreds of years, magnetic declination is observed to vary over tens of degrees. The movie on the right shows how global declinations have changed over the last few centuries. The direction and intensity of the dipole change over time. Over the last 2 centuries the dipole strength has been decreasing at a rate of about 6.3% per century. At this rate of decrease, a field would reach zero in about 1600 years. However, this strength is about average for the last 7,000 years, and the current rate of change is not unusual. A prominent feature in the non-dipolar part of the secular variation is a westward drift at a rate of about 0.2 degrees per year. This drift is not the same everywhere and has varied over time. The globally average drift has been westward since about 1400 AD but eastward between about 1000 AD and 1400 AD. Changes that predate magnetic observatories are recorded in archaeological and geological materials. Such changes are referred to as paleomagnetic secular variation or paleosecular variation. The records typically include long periods of small change with occasional large changes reflecting geomagnetic excursions and reversals. Magnetic field reversals. Although the Earth's field is generally well approximated by a magnetic dipole with its axis near the rotational axis, there are occasional dramatic events where the north and south geomagnetic poles trade places. Evidence for these geomagnetic reversals can be found worldwide in basalts, sediment cores taken from the ocean floors, and seafloor magnetic anomalies. Reversals occur at apparently random intervals ranging from less than 0.1 million years to as much as 50 million years. The most recent geomagnetic reversal, called the Brunhiser-Urumatayama reversal, occurred about 780,000 years ago. Another global reversal of the Earth's field, called the Lushamp event, occurred during the last ice age. However, because of its brief duration it is labeled an excursion. The past magnetic field is recorded mostly by iron oxides, such as magnetite, that have some form of ferromagnetism or other magnetic ordering that allows the Earth's field to magnetize them. This remanent magnetization, or remanence, can be acquired in more than one way. In lava flows, the direction of the field is frozen in small magnetic particles as they cool, giving rise to a thermoremanent magnetization. In sediments, the orientation of magnetic particles acquires a slight bias towards the magnetic field as they are deposited on an ocean floor or lake bottom. This is called detrital remanent magnetization. Thermoremanent magnetization is the form of remanence that gives rise to the magnetic anomalies around ocean ridges. As the seafloor spreads, magma wells up from the mantle and cools to form new basaltic crust. During the cooling, the basalt records the direction of the Earth's field. This new basalt forms on both sides of the ridge and moves away from it. When the Earth's field reverses, new basalt records the reverse direction. The result is a series of stripes that are symmetric about the ridge. A ship towing a magnetometer on the surface of the ocean can detect these stripes and infer the age of the ocean floor below. This provides information on the rate at which seafloor has spread in the past. Radiometric dating of lava flows has been used to establish a geomagnetic polarity timescale, part of which is shown in the image. This forms the basis of magnetostratigraphy, a geophysical correlation technique that can be used to date both sedimentary and volcanic sequences as well as the seafloor magnetic anomalies. Studies of lava flows on Steens Mountain, Oregon, indicate that the magnetic field could have shifted at a rate of up to 6 degrees per day at some time in Earth's history, which significantly challenges the popular understanding of how the Earth's magnetic field works. Temporary dipole tilt variations that take the dipole axis across the equator and then back to the original polarity are known as excursions. Earliest appearance, a paleomagnetic study of Australian red dacite and pillow basalt has estimated the magnetic field to have been present since at least 3,450 million years ago. Future. At present, the overall geomagnetic field is becoming weaker. The present strong deterioration corresponds to a 10–15% decline over the last 150 years and has accelerated in the past several years. Geomagnetic intensity has declined almost continuously from a maximum 35% above the modern value achieved approximately 2,000 years ago. The rate of decrease and the current strength are within the normal range of variation, as shown by the record of past magnetic fields recorded in rocks. The nature of Earth's magnetic field is one of heteroscedastic fluctuation. An instantaneous measurement of it, or several measurements of it across the span of decades or centuries, are not sufficient to extrapolate an overall trend in the field strength. It has gone up and down in the past for no apparent reason. Also, noting the local intensity of the dipole field is insufficient to characterize Earth's magnetic field as a whole, as it is not strictly a dipole field. The dipole component of Earth's field can diminish even while the total magnetic field remains the same or increases. The Earth's magnetic north pole is drifting from northern Canada towards Siberia with a presently accelerating rate of 10 km per year at the beginning of the 20th century, up to 40 km per year in 2003, and since then has only accelerated. Physical origin. The Earth's magnetic field is believed to be generated by electric currents in the conductive material of its core, created by convection currents due to heat escaping from the core. However, the process is complex, and computer models that reproduce some of its features have only been developed in the last few decades. Earth's core and the geodynamo. The Earth and most of the planets in the Solar System, as well as the Sun and other stars, all generate magnetic fields through the motion of highly conductive fluids. The Earth's field originates in its core. This is a region of iron alloys extending to about 3,400 km. It is divided into a solid inner core, with a radius of 1220 km, and a liquid outer core. The motion of the liquid in the outer core is driven by heat flow from the inner core, which is about 6,000 km, to the core mantle boundary, which is about 3,800 km. The pattern of flow is organized by the rotation of the Earth and the presence of the solid inner core. The mechanism by which the Earth generates a magnetic field is known as a dynamo. A magnetic field is generated by a feedback loop. Current loops generate magnetic fields. A changing magnetic field generates an electric field. And the electric and magnetic fields exert a force on the charges that are flowing in currents. These effects can be combined in a partial differential equation for the magnetic field called the magnetic induction equation, where U is the velocity of the fluid, B is the magnetic B field, and I equals 1/I florin I 1/4 is the magnetic diffusivity, a product of the electrical conductivity I florin and the permeability I 1/4. The term ABAT is the time derivative of the field. A2 is the Laplace operator and AA is the curl operator. The first term on the right-hand side of the induction equation is a diffusion term. In a stationary fluid, the magnetic field declines and any concentrations of field spread out. If the Earth's dynamo shut off, the dipole part would disappear in a few tens of thousands of years. In a perfect conductor, there would be no diffusion. By Lenz's law, any change in the magnetic field would be immediately opposed by currents, so the flux through a given volume of fluid could not change. As the fluid moved, the magnetic field would go with it. The theorem describing this effect is called the frozen-in-field theorem. Even in a fluid with a finite conductivity, new field is generated by stretching field lines as the fluid moves in ways that deform it. This process could go on generating new field indefinitely, were it not that as the magnetic field increases in strength, it resists fluid motion. The motion of the fluid is sustained by convection, motion driven by buoyancy. The temperature increases towards the center of the Earth, and the higher temperature of the fluid lower down makes it buoyant. This buoyancy is enhanced by chemical separation. As the core cools, some of the molten iron solidifies and is plated to the inner core. In the process, lighter elements are left behind in the fluid, making it lighter. This is called compositional convection. A Coriolis effect, caused by the overall planetary rotation, tends to organize the flow into rolls aligned along the north-south polar axis. The mere convective motion of an electrically conductive fluid is not enough to ensure the generation of a magnetic field. The above model assumes the motion of charges, which is a requirement for generating a magnetic field. However, it is not clear how this motion of charges is created in the circulating fluid of the outer core. Possible mechanisms may include battery-like electrochemical reactions that generate electrical current in the fluid, or a thermoelectric effect, or a triboelectric effect. More robustly, remnant magnetic fields in magnetic materials in the mantle, which are cooler than their Curie temperature, would provide CD-O stator magnetic fields that would induce the required growing currents in the convectively driven fluid behaving as a dynamo, as analyzed by Dr. Philip William Livermore. The average magnetic field in the Earth's outer core was calculated to be 25 Gauss, 50 times stronger than the field at the surface. Numerical models, simulating the geodynamo requires numerically solving a set of nonlinear partial differential equations for the magnetohydrodynamics of the Earth's interior. Simulation of the MHD equations is performed on a 3D grid of points, and the fineness of the grid, which in part determines the realism of the solutions, is limited mainly by computer power. For decades, theorists were confined to creating kinematic dynamos in which the fluid motion is chosen in advance and the effect on the magnetic field calculated. Kinematic dynamo theory was mainly a matter of trying different flow geometries and testing whether such geometries could sustain a dynamo. The first self-consistent dynamo models, ones that determined both the fluid motions and the magnetic field, were developed by two groups in 1995, one in Japan and one in the United States. The latter received attention because it successfully reproduced some of the characteristics of the Earth's field, including geomagnetic reversals. Currents in the ionosphere and magnetosphere. Electric currents induced in the ionosphere generate magnetic fields. Such a field is always generated near where the atmosphere is closest to the Sun, causing daily alterations that can deflect surface magnetic fields by as much as 1 degree. Typical daily variations of field strength are about 25 nanoteslars, with variations over a few seconds of typically around 1 nt. Measurement and analysis, detection. The Earth's magnetic field strength was measured by Carl Friedrich Gauss in 1835 and has been repeatedly measured since then, showing a relative decay of about 10% over the last 150 years. The MagSat satellite and later satellites have used 3-axis vector magnetometers to probe the 3D structure of the Earth's magnetic field. The later RSTED satellite allowed a comparison indicating a dynamic geodynamo in action that appears to be giving rise to an alternate pole under the Atlantic Ocean west of West Africa. Governments sometimes operate units that specialize in measurement of the Earth's magnetic field. These are geomagnetic observatories, typically part of a national geological survey, for example the British Geological Survey's Esquelmet Observatory. Such observatories can measure and forecast magnetic conditions such as magnetic storms that sometimes affect communications, electric power, and other human activities. The International Real-Time Magnetic Observatory Network, with over 100 interlinked geomagnetic observatories around the world, has been recording the Earth's magnetic field since 1991. The military determines local geomagnetic field characteristics, in order to detect anomalies in the natural background that might be caused by a significant metallic object such as a submerged submarine. Typically, these magnetic anomaly detectors are flown in aircraft like the UK's Nimrod or towed as an instrument or an array of instruments from surface ships. Commercially, geophysical prospecting companies also use magnetic detectors to identify naturally occurring anomalies from ore bodies, such as the Kursk magnetic anomaly. Crustal magnetic anomalies. Magnetometers detect minute deviations in the Earth's magnetic field caused by iron artifacts, kilns, some types of stone structures, and even ditches and middens in archaeological geophysics. Using magnetic instruments adapted from airborne magnetic anomaly detectors developed during World War II to detect submarines, the magnetic variations across the ocean floor have been mapped. Basalt the iron-rich, volcanic rock making up the ocean floor contains a strongly magnetic mineral and can locally distort compass readings. The distortion was recognized by Icelandic mariners as early as the late 18th century. More important, because the presence of magnetite gives the basalt measurable magnetic properties, these magnetic variations have provided another means to study the deep ocean floor. When newly formed rock cools, such magnetic materials record the Earth's magnetic field. Statistical models. Each measurement of the magnetic field is at a particular place and time. If an accurate estimate of the field at some other place and time is needed, the measurements must be converted to a model and the model used to make predictions. Spherical harmonics. The most common way of analyzing the global variations in the Earth's magnetic field is to fit the measurements to a set of spherical harmonics. This was first done by Carl Friedrich Gauss. Spherical harmonics are functions that oscillate over the surface of a sphere. They are the product of two functions, one that depends on latitude and one on longitude. The function of longitude is 0 along 0 or more great circles passing through the north and south poles. The number of such nodal lines is the absolute value of the order m. The function of latitude is 0 along 0 or more latitude circles. This plus the order is equal to the degree a. Each harmonic is equivalent to a particular arrangement of magnetic charges at the center of the Earth. A monopole is an isolated magnetic charge, which has never been observed. A dipole is equivalent to two opposing charges brought close together, and a quadrupole to two dipoles brought together. A quadrupole field is shown in the lower figure on the right. Spherical harmonics can represent any scalar field that satisfies certain properties. A magnetic field is a vector field, but if it is expressed in Cartesian components x, y, z, each component is the derivative of the same scalar function called the magnetic potential. Analyses of the Earth's magnetic field use a modified version of the usual spherical harmonics that differ by a multiplicative factor. A least squares fit to the magnetic field measurements gives the Earth's field as the sum of spherical harmonics, each multiplied by the best fitting Gauss coefficient GMA, or HMA. The lowest degree Gauss coefficient, GOO, gives the contribution of an isolated magnetic charge, so it is zero. The next three coefficients are G10, G11, and H11 determine the direction and magnitude of the dipole contribution. The best-fitting dipole is tilted at an angle of about 10 degrees with respect to the rotational axis, as described earlier. Radial dependence, spherical harmonic analysis can be used to distinguish internal from external sources if measurements are available at more than one height. In that case, each term with coefficient GMA, or HMA, can be split into two terms, one that decreases with radius as 1/Ra plus 1 and one that increases with radius as Ra. The increasing terms fit the external sources. However, averaged over a few years the external contributions average to zero. The remaining terms predict that the potential of a dipole source drops off as 1 per Rankine 2. The magnetic field, being a derivative of the potential, drops off as 1 per Rankine 3. Quadrupole terms drop off as 1 per Rankine 4, and higher-order terms drop off increasingly rapidly with the radius. The radius of the outer core is about half of the radius of the Earth. If the field at the core mantle boundary is fit to spherical harmonics, the dipole part is smaller by a factor of about 8 at the surface, the quadrupole part by a factor of 16, and so on. Thus, only the components with large wavelengths can be noticeable at the surface. From a variety of arguments, it is usually assumed that only terms up to degree 14 or less have their origin in the core. These have wavelengths of about 2,000 km or less. Smaller features are attributed to crustal anomalies. Global models. The International Association of Geomagnetism and Aeronomy maintains a standard global field model called the International Geomagnetic Reference Field. It is updated every 5 years. The 11th generation model, IGRF-11, was developed using data from satellites and a world network of geomagnetic observatories. The spherical harmonic expansion was truncated at degree 10, with 120 coefficients, until 2000. Subsequent models are truncated at degree 13. Another global field model, called World Magnetic Model, is produced jointly by the National Geophysical Data Centre and the British Geological Survey. This model truncates at degree 12. It is the model used by United States Department of Defense, the Ministry of Defense, the North Atlantic Treaty Organization, and the International Hydrographic Office, as well as in many civilian navigation systems. A third model, produced by the Goddard Space Flight Center and the Danish Space Research Institute, uses a comprehensive modeling approach that attempts to reconcile data with greatly varying temporal and spatial resolution from ground and satellite sources. Biomagnetism. Animals including birds and turtles can detect the Earth's magnetic field, and use the field to navigate during migration. Cows and wild deer tend to align their bodies north-south while relaxing, but not when the animals are under high-voltage power lines, leading researchers to believe magnetism is responsible. In 2011, a group of Czech researchers reported their failed attempt to replicate the finding using different Google Earth images. See also: geomagnetic jerk, geomagnetic latitude, history of geomagnetism, magnetic field of the Moon, magnetosphere of Jupiter, magnetotellurics, Carnegie, Galilei. References. Further reading. External links: Geomagnetism and Paleomagnetism background material. American Geophysical Union Geomagnetism and Paleomagnetism section. National Geomagnetism Program. United States Geological Survey, March 8, 2011. BGS Geomagnetism. Information on monitoring and modeling the geomagnetic field. British Geological Survey, August 2005. William J. Broad, Will Compasses Point South? New York Times, July 13, 2004. John Roach, Why Does Earth's Magnetic Field Flip? National Geographic, September 27, 2004. Magnetic Storm. PBS Nova, 2003. When North Goes South. Projects in Scientific Computing, 1996. The Great Magnet, the Earth, History of the discovery of Earth's magnetic field by David P. Stern. Exploration of the Earth's magnetosphere, educational website by David P. Stern and Mauricio Peredo Drive Dan Lathrop, The Study of the Earth's Magnetic Field. Interview with Dr. Dan Lathrop, geophysicist at the University of Maryland, about his experiments with the Earth's core and magnetic field. July 3, 2008, International Geomagnetic Reference Field 2011, Global Evolution Anomaly of the Earth's Magnetic Field Sweeps are in 10-degree steps at 10 years intervals. Based on data from the Institute of Geophysics, ETH Zurich.